Well, thanks very much. I take a lot of latitude in that term leading. So I'm going to talk a little bit about some work that we just started last August, and so it's pretty new, and we're trying to, kind of get it moving here. So we met last August in Columbus, Ohio. There were 16 of us, research and policy experts, to talk about how, and this was focused in Ohio, the Lake Erie issue, how to better use our field phosphorus data that's being measured. There's quite a lot of it, great data that's being collected in Ohio. And how do we use that with our models to talk about and research fate and transport, to more effectively reduce agricultural phosphorus loss, get at topics that Bruce talked about. So we had some presentations. We talked about soil test phosphorus measurements, fertilizer recommendations, these topics that just seem simple but don't go away. Trends in edge of field in-stream water quality observations, the data that's being collected, and some of the models we have to start to simulate soil phosphorus fate and transport. So we identified 3 areas that we could do some research on moving forward as a group. One was this question of legacy versus incidental phosphorus loss, identifying hotspots in the landscape of elevated phosphorus export, and then coupling models for production of organic residuals, recovering phosphorus from wastes, and coupling those with watershed models to look at fate in that whole recycling system. So what I was going to do is talk about these things, some of the work that we've kind of done on those before that could be applied to these topics, and how we might use those methods to get at these issues. So we had, again, our 3 topics. We have a team lead for each of these, and a great group of people working on each of these topics. Some of them are in the room today. So our first topic was looking at this question of legacy versus incidental phosphorus loss. Just a little definition. This is an example of data where we're looking at these black triangles here might be our legacy phosphorus loss, phosphorus that's coming out of the soil, sort of at this low base level. We apply manure, we get runoff shortly after, we get these high rates of phosphorus loss that decline very rapidly. So, you have these 2 sources here, and we wanted to understand what's the relative contribution of each to phosphorus loss in the landscape. If we were going to manage these 2 different sources, which is more important to manage, and so how can we get better information to help us manage better? So what we want to do in attacking these issues really is we want to use our field data, combine our field data and our simulation models to tell us how to best manage these 2 phosphorus sources, for example. So basically what we want to do is be using our field data. Our field data obviously is being collected with certain treatments, certain scenarios, so it's limited in what we can say. But use our models and the field data, testing our models with the data, and then use the models to expand our scenarios and our scales to understand what's happening from the field up to the watershed scale. So I think we have a pretty unique opportunity right now, because in the last 10 years or so, we've really been harmonizing our models and some of the phosphorus routines that are in these. So we have now a series of models. We have the Apple model, which is a very user-friendly spreadsheet type model, field scale. It's really rapid to explore different scenarios. And then we move up in complexity to our Surfos model, and that is a daily time step model that needs some more data, some more complexity, but we can get at this incidental phosphorus loss. Compared to the Apple model, which is an annual time step, so it's a broader time scale. And then we get up into the SWOT model, which is a watershed scale model, so we can look at where things are happening in the landscape and that transport to a water body. So what's nice is these will vary in complexity and ease of use, but they're all using the same equation. So you should be able to get the same sorts of answers out of them. They're going to be consistent in the information they're going to tell you, but they're good for different reasons. So some of the examples of how we use these models so you get an understanding of what they're good for. For example, this is an application of the Apple model. So this is a spreadsheet model, annual time step, very easy to use. Looking at if we could reduce soil phosphorus in all the agricultural land in Maryland. They've made a big effort in the last several years to do a lot of soil testing in Maryland and quantifying how many of their soils and where they are high in phosphorus. So we applied the Apple model to say, given this distribution and the amount of land that has this phosphorus, if we could draw all those high phosphorus soils down to an agronomic optimum basis, what's the potential to reduce phosphorus loss from those ag lands? So this is very rapid to do, very easy to do with this type of model. And what's very interesting, I think, is so this red line on top is where we are right now. The green line would be if all the soils were at agronomic optimum. And the blue line is what the model is telling us if we just draw down soil phosphorus through crop removal, or how long it's going to take us to get to that green line. It's a very slow process, but I see that there's huge potential, 40% less phosphorus loss by just being at optimum across the watershed. So this is a good example of the kind of things that we could do in Ohio, looking at very rapid type of estimates. And they kind of give you targets for potentials. Is the legacy phosphorus a big issue? What's the potential to make improvements on that front? So going up to this legacy versus incidental phosphorus loss issue, we get into our use of our SURFOS model application. This is a daily time step model, so it's good for simulating manure or fertilizer application, what happens in storm events immediately after application. So this is an example of how we could apply that model. This is some work we did in Wisconsin looking at if you applied manure on a given day of the year, what would be the potential for phosphorus loss just from that manure application. And we looked at data. So the graph on the left is showing if you had high, medium, or low runoff fields, and each dot in that graph is representing what would be the phosphorus loss if manure was applied that day. And we run this for 30 years of measured runoff data that we have in the state. So we can start to get an idea of what times of years are worse than others for manure or fertilizer application. And I think what's very interesting is when you get to the table on the left, we can look at seasonal differences, and we can look at differences in fields that are low potential for transport versus high. And we can start to quantify, in the far column on the table, soils that are fields that are high potential for loss. We can get targets. There's 7 times more phosphorus loss out of those types of fields. Or it's seasonal differences. If we could get manure applied more in the summer, then we could potentially reduce our phosphorus loss by 3 to 4 times. So this is what's good about this type of model, to be able to look at that incidental. So we have those 2 models, Apple and SURFOS, and then so those are both field scale models. So I'm not going to look at where is this happening in the watershed. So if you want to scale up to the watershed, we would use our SWOT model then to say spatially where are these things happening and what does that mean for the loads that are actually getting to the water body at the outlet. So our second topic that we looked at during this meeting was identifying phosphorus hotspots in the landscape. So this would be areas where they have a high potential for phosphorus loss, higher than other areas. Some of the there again, one of the applications that we've done something similar, we get back to the Chesapeake Bay and Maryland agricultural example. In doing that, I showed earlier with that potential for phosphorus drawdown. In doing that effort, you look at the data that's coming out of soils, and what you see there in this table, if you're adding up these numbers, we're seeing that 18 to 19% of the land area that they're measuring is above 150 parts per million in soil test phosphorus, which is in Maryland what they say you have to start applying their phosphorus index rules and dealing with the phosphorus that you may apply. So 19% of land is above 150, but that's responsible for 37% of the legacy phosphorus loss. So you can get an idea of where these things are happening, what is the relative contribution of soils that are very high in phosphorus versus areas that are lower in phosphorus. And so it gives you the ability to set targets, but also identify areas that are best to target for management. So again, these are things that we could want to use these methods to apply to watersheds in Ohio. So when you talk about hotspots, so that would be an example of where soil phosphorus, legacy phosphorus, areas that are high in soil phosphorus from historical applications higher than other areas. So when you talk about hotspots, there's also the incidental phosphorus. So this is phosphorus loss from recently applied manure or fertilizer. And these could be considered temporal hotspots, right? Those events soon after application. What if we could avoid those kind of events? Apply manure at a time, or if it's going to rain and you're going to get runoff, skip that storm, wait a few days, apply manure the following week. So this is an application we used, again, the Surfhouse model. We looked at this idea in Wisconsin, again, with some of the same data that I showed before. So this table is basically showing that we look at over 30 years of weather data. We're seeing that the average annual phosphorus loss from manure applied is 1.25. If we would have so we told the model, if there's runoff on that day, skip that day, wait for the next time where there's a 2-day window where there's no runoff. What would be the phosphorus loss? So we're skipping that immediate runoff event. So we can get, what you see is very interesting, I think, is that you can get small reductions in phosphorus loss by skipping those storms. But the number of days here in this second row that provide those opportunities, I thought was lower than I might expect. And so, and the phosphorus loss that you see in that first row doesn't seem to be all that great, the reductions by skipping those storms over 30 years, averaged over 30 years of weather. But you can see, like in this third row here, any given event, by skipping a big event, can make a big difference in any year. But over a long time period, maybe that incidental loss is not providing us a lot of opportunities to attack the phosphorus loss issue. So this is very interesting type data. These are the things we can look at fertilizer applications and timings in Ohio, and try to understand better what kind of management is important, what kind of management gives us the biggest opportunities to look at phosphorus loss control. Again, this data is field scale, trying to then scale this thing up to the watershed, saying in these fields, if we're doing these things in this amount of area, what does that mean for phosphorus loss at the outlet? So our third and final topic that we looked at is coupling phosphorus production models to watershed models. So this is the idea of coupling nutrient recovery process models that may be used in wastewater treatment plants, for example, with SWAT, the hydrologic model. So the idea of if you're recovering phosphorus and it's in certain chemical form, and then you're using that phosphorus in the landscape as a fertilizer, given that chemical makeup, what's the potential for loss in runoff and diffuse sources? So some of the expected benefits of being able to do those types of simulations, the potential to simulate and optimize nutrient behavior over the whole production and application chain. And the potential then to adjust the fertilizer quality that has the biggest benefit at the watershed scale. So again, this is just a schematic of what kind of, how that research might go. So you have a nutrient recovery process modeling that's going on. That's recovering a certain type of fertilizer with characteristics. You're saying with the SWAT model that fertilizer is being applied in the watershed. You're looking at the phosphorus loss from that type of fertilizer at certain rates, certain areas. You're looking at the loss then. and you're trying to communicate between the two models, then, well, what if we're changing this nutrient recovery process or chemistry? What does that mean for phosphorus loss then at the watershed? And trying to optimize those types of processes. So there are some research needs in this, development of SWOT routines to allow for more advanced chemical representation of the fertilizer materials and runoff. This gets to a lot of work that I've done personally, just looking at these models, improving them for what we want to do. This would be, there aren't good routines in SWOT right now for that, so that would be a research need. And then developing that interface between the nutrient recovery model and SWOT, allow for that data exchange and optimization. So that would be the third bullet point there too. So that's a quick overview of what we did, the topics we identified in this group. We've had some progress of looking at our methods, getting some data, field data together, starting to analyze some of that. This is a slow project just because we're all very busy with things, but we're trying to keep progress on it and keep together and keep moving on this, because I think there's a lot of potential, and I think we have really good methods and models now to attack these in a very systematic way. So I would be glad to answer any questions about that.
Making this hard on me, Carl. Excuse me.
Great talk, Pete. One of the questions I had is the results of the model, where you showed that even after 6 days of the manure, I guess, presumably surface applied, but there was a minimal reduction in the incidental losses. Are those model results consistent with what people have shown in actual field experiments? I mean, was there any type of looking at trying to corroborate what the model was saying with what, experimental data show?
Yeah, that's a great question. I think that gets at the idea that those sorts of things can be really hard to do with field data, because you'd have to have these controlled sort of experiments. And there has been some of that, but it's been very limited. I don't know that there's been, I can think of maybe one paper that's sort of looked at what if you skipped some rainfalls, and so there has been a little bit of data. I was really surprised at that. So I think I still struggle with how to talk about those data, because I think over the long-term average, we're not seeing a lot of potential there through the model. But in any given event, that if you miss a big event and applied manure after that, that can be really beneficial. So you don't want to tell people that, hey, just put it out whenever you want. But it is important to understand relative to legacy phosphorus in the soil and those things, what kind of potentials are we really talking about? Because in fact, when you get into a lot of the phosphorus indexes that are used in the country, they're formulated to sort of attack that manure application issue and the risk of phosphorus loss from those sorts of things. And they don't necessarily include that legacy P issue as well. So I think this is still kind of fresh information that I'd really like to pursue a little bit.
Excellent talk. I really enjoy your talk. Just curious about the legacy versus incidental phosphorus. How do you separate those two different type of phosphorus once they come down to the open waters or watershed?
Well, that's one of the things that we talked about at the meeting. In measured data, that's very hard to do. Where do you draw a line that says one signal is, when does it become part of the soil that we consider it now legacy P? In the model, well, that's easy because we're simulating these different pools of where things are coming out of, and we quantify it. So the idea really is, let's run the model, let's compare it to our field data. We are setting up and building these models so that the processes that we are in there, we are very confident that they're simulating what we know is happening in the field. you're testing the models, you have confidence that they're simulating the conditions that you've measured well, and then you allow the model to give you that information that the field data can't. So that's the idea, and that's when it gets, to me, in my mind, very powerful to start to combine the modeling with the field data. Not to try to get all your answers out of the field data, but use the models appropriately and make sure that the equations are doing what you want. I think you get really great information out of that complementary process. Sorry.
Hi, thanks. Question about the legacy phosphorus and the watershed scale analyses that you're doing. The SEEP cropland assessment for the Western Lake Erie Basin, the SWAT model report on that, Jeff Arnold and Mike White's work, looked at legacy phosphorus and found that legacy phosphorus actually in the watershed, in the stream network, was also very important. And obviously a factor that's pretty difficult to control. So as we think about making progress on these water quality challenges that we have, is your group working on how we can better assess in-stream sources of legacy phosphorus, moving beyond the edge of the field where we can do a little bit more with it?
No, that's a great question. I'm glad you asked that because it adds some context. So like the Apple model, the Surfos model, they're just edge of field. So that's looking at controlling what you're doing in the field. So something like SWAT would then add in those channel processes. Potentially, I'm not sure about probably not the water body processes. Maybe it does some of that. I'm not an expert in that. I would say, though, that probably the science that's in that model for those things is maybe less mature than what's in the field side of it. So there's good research to do there. I've always been surprised in my career how slowly the physical research finds its ways into models and those routines, because those people often don't talk well enough. They don't, you don't get people who are doing the research who actually even understand what the models are doing. So if we could, this was what was great, I think, about this effort, is to get those people in the same room working together, and we get a lot of better outcomes.
And one more quick question, if I can. So I'm wondering how the development of SWAT Plus is going to impact some of these field-to-watershed linkages going forward, given that it's now going to be very different in terms of the way it processes or simulates processes than it has been in the past.
So from what I understand in that process was really, like models, it's very important to take them to the next level, next generation. You always have to improve them, not just with the equations, but how they function. So that's been a big effort to just make it easier to use, to functionality, a lot more object-oriented. And so I don't know that they've changed the science equations under there that are, but it is, I think, probably a lot better in being able to say where things are happening on the landscape and move things through these different channels and ending up in the water body. So from what I understand, it should be a great improvement to people who actually use SWAT. So, yeah.
Okay, probably last question here. Sorry.
I had two questions. One related to SWAT and Lake Erie. So have you given thoughts to maybe linking up with aquatics folks and microbiologists and take your modeled phosphate flux into Lake Erie and use it as a HABs predictor?
I don't think we talked about that. That's obviously the logical thing to do. In my career, I've been up in the landscape with the science and the modeling there, so that's what I've focused on. There's a lot of opportunity there without bringing in the water body, but of course the whole system is critical to understand and couple.
My second question on the modeling of the fate and transport of phosphorus. Don't you need to differentiate between particulate phosphorus and dissolved phosphorus?
Yeah, great point. And so all these models are doing that.
Like the 1.2 kilograms per hectare. Is that total?
Yeah,
And
so
if it's
all
to-
those numbers that you saw were total P. So that's a combination, but the models will differentiate, and so they can tell you how much is dissolved, how much is. And I would just say that, you know, we've done a lot of work to calibrate and verify these equations for phosphorus in there, and we're feeling really confident with them.
Yeah, so on the follow-up on your waiting for days between the rain events, you had the 1 point something. So do you offhand know the ratio of dissolved phosphorus to total phosphorus?
Yeah, good question. Well, so that was so for those incidental losses, that was just soluble P. So that's just soluble P coming out of manure that's on the surface. Just for the incidental losses of manure on the surface, that's all dissolved P. So that's not manure particulates moving or soil or anything. That was just manure. Yeah, great. I blew through that stuff, so you know there's a lot of details there that I'd be happy to talk about with anyone. So.
Thank you. Great, let's thank Peter.